Hello, welcome to Evangelistic Apologetics, an introduction to systematic Christian worldview. We are on our third section, the great section, which is called The Science of Science. And within that, we are on our fourth lesson, which is called The Scientific Standard for Theories. Okay. We have learned that science is basically man's study of nature. And we study nature with our experience and with reason. Okay? And in science, we try to minimize the place of faith, which is top down. But overall, we have three ways of knowledge: faith, to know the supernatural; reason, to know the human level; and then experience, to know the natural. Science is our knowledge of the natural world, and basically it's based on experience. But it is related to reason, and somewhere it actually relates to faith. A lot of people want to minimize that, but it is there. We just make it small. Okay? Therefore, today, as we are studying the scientific standard for theories, we must recognize the nature of science. We are seeing everything, like a pyramid. At the bottom is experience. And science is heavily based on experience. All of the authority of scientific theories, especially the mature ones that can be applied, their authorities are based on that these theories have been validated by experience, by experiments. Okay? Since they can be repeated and they have been validated, in other words, if you repeat it, it's going to be the same. Okay? You're going to expect the same result. That's why it can be applied. It can benefit people's lives. So if science wants to be authoritative, it must have empirical evidence. Okay, so when we face a theory, somebody comes here and say, I have a scientific theory. Okay, and you're going to evaluate the theory, number one, by looking for whether or not you can have proof. And the proof is bottom-up proof, is by experience, by experiments, in other words. So the scientific standard for theories, number one, will be proof. Okay? The proof is experimental validation and, well, if not, then it's falsification. As we learn, if a theory that can be it's about something that can be repeated, can be experimented on, then you just, first of all, you make up the theory by what you already experienced from the specific situations. Specific situations. You say, okay, let's make something general, let's make a theory. And the theory will expand out into something that you have not experiment yet, and now you make an experiment. Okay, so the making of the theory is called the logical process of induction. Okay, and once you made a theory, then you make a deduction. Induction is from specific to general, deduction is from general to specific. And then you go and experiment. You either validate it, you falsify it. Okay? And if the theory is falsifiable, the theory is scientific. If it's not falsifiable, in other words, you can't test it, then it's not scientific. Okay? It's just a philosophy. And if the theory is scientifically falsified, well, you say, okay, let's cut to another place. Maybe and that place, it will be validated. You see? So the proof is when you have experimental validation. You predict this thing will happen, and you do an experiment, and it really has only two options. It happens or does not happen. If it does not happen, you falsify the theory, then you change the theory. You kind of restrain its range and until another range, maybe smaller range, and then you test it, and then once you validate it, you say the experiment agrees with the prediction, then the theory has been validated. Okay, so the experimental validation is a proof of a theory, and sometimes you can. What if you cannot validate the whole thing? You know, if the theory is about a small scale situation, let's say all of the chairs in my room are of the gray color. Well, that's a small scale thing. I can validate it by counting them one by one, but it doesn't really mean anything. But if the scientific theory is about something grand, let's say all of the sea water in the oceans of the sea have the salt level above a certain level. That's a prediction. Well, you know, when you are near the mouth of a river with fresh water, that salt percentage is going to be lower, right? And if deep in the ocean, it's going to be higher. So you have to say, well, average is so and so, okay? But you know at the mouth of the river, it's less. And so when you give the restrictions on, okay, the level in the sea is so and so, but you have to exclude the mouth of the river. Well, that is the restrictions, the boundaries on your theory. And sometimes you have to have assumptions, you know, behind the theory. You must state it, okay? And you make it explicit. Don't hide your assumptions. Okay? For example, the current theory of the Big Bang theory of the universe. Okay? We assume that Einstein's theory of general relativity is correct. Okay? He assumes that gravity is equal to a system that's accelerating. So if you stand in the accelerator and let's say in an elevator, the elevator accelerates up above, you know, going up, then you're going to feel a force on you, right? And that force is like gravity. Okay? And so that equivalence principle is the foundation of general relativity. You have assumed that this equivalence principle is true. That's your assumption. Okay? And you add this assumption to the Newtonian physics. Okay? Newtonian physics, you add let's say, the speed of light being the same in all reference systems. From there, you get the special relativity. Once you add these equivalence principle of the gravity is equal to the acceleration of the system, then you get general relativity. Okay? All of these theories have assumptions behind. You must state them in the front. But the current Big Bang theory actually has one more assumption added to it. You see, just by Einstein's theory of general relativity, you can only have two kinds of universe. Okay? Either an expanding universe or a contracting universe. You never have a static universe. Okay? And Albert Einstein thought very bad about it. He didn't like an expanding universe. He liked a static universe. So he put in a constant. He's trying to make it static. But he later admitted that was an error. Because later there's somebody who's called Edwin Hubble. He found out the universe is expanding. Okay? And the speed that determines the redshift of the light is proportional to their distance. In other words, the further the stars are, the faster they're leaving us. Okay? And that Hubble's law, once it's considered a validation of one kind of solution of Einstein's equation. And thus you have the expanding universe theory. However, that's not all. Because the expanding universe, from the evidence we have now, all of the stars and galaxies are leaving our galaxy, the Milky Way. In other words, we seem to be in the center of the universe. All other galaxies are leaving us isotropically, like in a sphere, they're leaving in the radial direction. And we are in the center. And this actually is the best evidence we have now from all observations. But that made some people feel not good. Some people feel if the universe has a center, then it will support creationism. And because of theological objection to that, they say, let's add in one more principle. They call it the Copernican principle, in honor of Copernicus, who discovered that the sun rather than the earth is the center of the solar system. And from there they extrapolate, they say there is no center in the universe. The universe has to be uniform, and all points in the universe must observe the same phenomena, that everything else is leaving them isotropically. How can this be done? We don't know. They do just make analogies that this is like on a sphere. If you blow a balloon, okay, and they say the relativity is about 4 dimensions, 3-dimension space plus 1-dimensional science, right? So they say the 4-dimension is hard to imagine, but assume that in a 3-dimension that you have this balloon, you blow it, it gets bigger. It's like expanding universe. And assume you are 2-dimensional people, you just live on the surface of the balloon. Then every spot on the balloon will see everything else leaving them uniformly. That is their analogy. Okay? They can only use an analogy. But the evidence we have now, through all of the observation, is that the Milky Way galaxy is the center of the universe. It's not that the Earth is the center. It's not that the sun is the center. The Milky Way is near the center of the universe. That's the most up-to-date scientific evidence for now. So this should be enough. But because of theological reasons, people added the Copernican principle that there is no center of the universe. So that's where the current theory of the Big Bang theory is based on. Okay, and we must tell that it added an unnecessary principle, and it is not clearly stated, and that is intellectual dishonesty. Okay, we must state clearly all the theories are based on some kind of axiom system, okay, assumed principles, okay, like the Euclidean geometry is based on the 5 axioms, or 4 if you are in spherical geometry. So you have to give the assumed principles, okay. So the proof, we must clearly state assumed principles. In other words, it will be dishonesty, okay? But with these stated, then you can have your theory, you can make your prediction, then can either validate or falsify, and once you falsify it, you change the theory, then you validate it, then you have a proof, okay? Once you have a proof through experiments, through experience, and this thing can be repeated, okay? Now, one person say, I have a theory, and the other people will validate it. Once they can repeat it, okay, this theory is proved. Okay. But there are some times when this thing cannot be proved beyond the reasonable doubt. You have experiments, but they can have ranges or rooms of interpretation. Okay. And sometimes you cannot you cannot validate the theory by doing experiment on everything, since it's so big. What you can do is you take samples. Okay, you take a few, let's say the saltiness of the ocean. You can take samples in the Pacific Ocean, in the Atlantic Ocean, and so on, and in the deep in the ocean, and in the surface near the mouth of water and away from mouth of water. You can take samples, and then you get a general picture. Okay, so in that case, you're not giving proofs, but you are giving evidence. So number 2, it will be evidence. Okay, so proof is kind of the final thing, nail in the coffin. Evidence is you can't nail it, but you can say, I have a probability that this thing is true. Okay, so what you do is you examine the probabilities of each inducted result, and you differentiate strong and weak evidences, and you state how believable the theory is. Okay, so you calculate, in this case, probabilities. Probabilities. Okay, and if a theory has a high probability, okay, that means it's more than 50%, then the theory is credible. If it has small probability, then it's not credible. All right. So when you make some prediction, not everything is true because it's 100%, because the system may be complex or too big. If you take samples to measure, you get the probabilities. If the probability is greater than 50%, then you say it's probable. Okay. And you measure the strong. You differentiate the strong versus weak evidence. Because the strong evidence usually leads to your conclusion in very few steps. The weak evidences will have to go through several steps, a long train of thought. In that case, if anything gets broken in the middle, then you don't end up at the end of your conclusion. Okay, so you got to distinguish them. Okay. Let's say, for example, you see that the animals, let's say there are apes and there are a man, and man walks straight and ape walk that way. And we have seen people that put the sequence, and draw differently. They say because there are similarities, there must be a genealogy and linkage, biological linkage between them. Well, no, similarities are not necessarily equal to biological lineage. Okay? And that is a weak evidence. Okay. A strong evidence is DNA. Okay, that's if two people have the same DNA, the probability is very small. They have to be twins from the same egg, and then they have the same DNA. Other than that, it's almost impossible. So we have strong evidence. We have weak evidence. When you think about the probability, you got to differentiate them in order to determine how much faith you put on this theory. Okay. Once it's proven, yeah, no problem, 100%. If it's not proven, you only have probabilities, then the higher the probability, then the more credibility you lean on it. Okay, you give it, and the more faith you put on it. Okay, so all together, these two are the empiricist side. Okay. These two together are basically the empiricist. Okay, empiricism. EMPRICISM. Okay, empiricism, because that's based on experience. Okay, again, we have three ways of knowledge. The lowest way is experience, and science is based on this. Okay, but science is also related to to reason, and that's the next two standard. But it's not just empiricism; it's also a realist empiricism. That means you believe there is a real world, there's a real existence of the world that's independent of our thought. We think or not, the sun exists. Okay, and a realist is not gonna restrain everything to only what I experienced exists. That is extreme empiricism. If I don't see it, it doesn't exist. Okay, like people say, God, if you exist, let me see you. If I see you, I believe you. If you don't let me see you, then you don't exist. Well, that's extreme empiricism, because what you don't see, sometimes they do exist. Okay, and like well, God, angels, demons, heaven, hell, and so on. Those things. So you cannot exclude it, at least. So a realist is an open-minded empiricist. Okay, there are realities beyond my perception, but the surety of my theory is based on my experience. If I experience it, I'm sure about it. If you haven't, then well, it may be there. I'm not closed-minded, but I'm not sure. I leave the possibility, but I only believe the ones with a high probability. Okay, and that is a realist empirist. So this is how the first half of the scientific theory, it's the standard for the theories, it's based on the empiricism. Okay, and that's half of it. But the other half of it is the third standard. Okay, so you see theory from bottom up by experience. How about top down? Well, top down is that the third standard. It's called compatibility. Okay, compatibility. Okay, so it must be compatible. Any theory must be compatible or in agreement with known, proven, or accepted theories. Okay, so they must be agreeing with the proven or accepted theories. Okay, in other words, you do not change the whole paradigm or framework. Okay? Scientists think like normal people think. We have assumed the worldview, a system, and the paradigms are hard to change. And remember, before Copernicus and Galileo, people just the ancient Greek science was just based on experience. Okay, and they see the sun and the moon rotate around the earth. Okay, the sun, the moon, the stars, and the planets, they all rotate around the earth. That is real empiricism. Okay, and that's what you see, and that's something that is real. It's almost like proven. Okay, however, the later Copernicus found out if you put the sun in the center, then the whole thing is simpler. Okay? And because the planets, the word planet actually literally means wanderer, because they wander. They sometimes go with a retrograde motion. Okay? And you see, Mars go this way and sometimes go back way and then go forward. So how do you explain that? That is, most people just think that is a live thing. It's free. And then he thought, okay, it has pretty regular. So it was a genius of a guy named Ptolemy. He thought that they have the motions in the circular motion with a smaller circle called epicycles. So they go like a cycle with an epicycle. You put them together, then you can explain that retrograde motion. But even that is not so good, so they have to put epicycle upon epicycle. The theory gets more and more complex. And Copernicus, he just thought, hey, if you change the system, just look from the sun's point of view, and then everything looks simple. Everything rotates in, he thought it was a circle around the sun. But later I found out it's not circle, it's an ellipse. It's mostly close to a circle. So from Copernicus then to Newton, who explained it dynamically, then that's how you get a new system. It's a solar-centered, okay? It's a heliocentrism. That is change of paradigm. Newtonian physics was very successful, and then when Einstein changed, changing to relativity, that's changing paradigm. And then quantum mechanics, it's another change of paradigm. Changing paradigm is hard, and you're not supposed to do that all the time, okay? You try not to. Okay? And therefore, there's a requirement. New theories, new guys on the block, you must agree with the big guys that's already here. Okay? And the accepted one sometimes could be wrong. But the proven one, you're not going to overthrow. Okay? So that is the compatibility idea. Okay? A new theory must agree with the existing one, such as, okay, we have many levels of laws. We know for natural science, we have physics, which is a foundational, and then you have chemistry, which is for bigger molecules. You have chemistry, and for really big molecules, you have biology. Okay, and for biology that has life and then it has intelligence, well, you have what? You have medicine, and you have physiology, and then you have psychology. And above psychology, then you have sociology, and then above sociology, you have, well, other things. You have politics, you have economics, and you have, above all, theology. Right? So there is a pyramid of all knowledges. I used to think, lower level can just reach to higher level. No, they don't reach. They cannot derive it because system is too complex. You cannot derive them from a lower level. Okay? I tried to be a physicist first and derive everything else. Well, I found that my intelligence will never be enough. I never lived long enough. Maybe live infinity of time. In the future, I could, but now, not in this lifetime. So what we have to accept that in each level of science, of knowledge, they find their laws through their observation, validation, and so on. Okay, and however, the higher level of laws do not contradict the lower levels of laws. Okay, so in agreeing, okay, not necessarily derived by, but in agreement with, not contradicting. So in other words, okay, biology is higher than chemistry, which is higher than physics. However, in the physics, the second law of thermodynamics, which means all systems, closed systems, cannot become more complex by itself. It has, if you want to be more complex, you have to input information. Otherwise, all closed systems naturally become less complex, more simpler and simpler, and that's called second law of thermodynamics. Okay? Entropy grows with time, order decreases with time. So higher levels of laws, like in biology and so on, they cannot contradict the lower levels of laws. Okay, and because those are proven laws, you're not going to overthrow it. Okay, and that's one issue. That's the third standard, the compatibility. And the fourth standard is, as I already mentioned, is the issue of beauty. B-A-U-T-Y, okay, beauty. And what is beauty in science? Beauty is basically simplicity. Okay, and if you have less assumptions, the less assumptions, the better. Okay, and because if you have many assumptions, if one of them break, the whole thing break. Okay, the less assumptions, the more reliable the theory is, and then you want more applications. Okay, because every application is a validation. Okay, the more places you validate, the higher the probability it is true. Okay, and then you have a simple structure. Okay, simple structure. So that is, the theory is not too complicated. That does not have too many winding roads. The simpler, the better. And in that way, the simplicity is the beauty of the theory. Okay, and the best example for beauty in science, I think, should be given to we should give the crown to Einstein's theories of special and general relativity. Because from Newtonian physics, okay, which is basically the three laws of Newton, and based on those three laws, and plus the general gravity, he can derive the motion of the solar system, and it was beautifully accurate. And so it has not many assumptions, just the three Newtonian laws, and then it has applications, almost everything in normal life. Einstein came in, he says, well, Newtonian physics breaks down with high-speed things close to the speed of light. Well, in that case, let's just add one assumption, that the speed of light is the same in all systems of reference. Okay? Just one assumption. Well, here has special relativity, and it is validated anywhere it can be tested. So very few, just adding one assumption, and it's a wide application, and it's validated. And the theory, well, it has this, difficulties. More and more, it's generally it's a simple thing. And the general relativity, you just add one more assumption, that the gravity is equivalent to the acceleration of a system. Then you have general relativity. And it has been it has been tested in only 3, or maybe you added the gravity wave, you have 4, no more than 4 cases where the general relativity interprets the evidence a little better than the Newtonian physics. So in other words, it has a few applications, not correcting all the time, but there's nothing contradicting to it. So general relativity is not as proven as the standard, as the special relativity, but it's still a beautiful theory. In other words, it's simple in its core. Okay? And it needs some improvements. Right now, there are 2 ways of improving it. Yeah, and that is what we believe is necessary. So all of these together, this is a theory which is rationalism, because we believe on reason. Okay, and we don't just depend on experience, we also need reason for science. And this rationalism is a reductionist. Reductionist means we want it to be as simple as possible. Okay? And there is a philosophy called the Occam's razor. William of Occam, he said, if you can use a razor to cut off the unnecessary assumptions, the more you can clean it, the better. That's the standard for the scientific theory. Amen.